Have you ever found yourself staring into the night sky, wondering about the fundamental mysteries of the universe? Or pondering about what the future of technology might look like? You're not alone. You're on the precipice of understanding one of the most revolutionary advancements in technology, and it's right here, in our hands. No, it's not the latest smartphone, but something far, far more powerful. Quantum computers. Now, I know what you're thinking, quantum, what? But don't worry, it's not as complicated as it sounds. And that's why we are here, to delve into this mysterious, mind-bending world and make it easy for you to understand. In our Quantum Computers Crash Course, we're going to journey into the heart of these incredible machines. We'll explore the qubits, learn about superposition, entanglement, quantum gates, and much more. And don't worry, we'll break down these complex terms and ideas into easy-to-understand concepts. Because that's what we do best. Before we dive in, hit that subscribe button and turn on notifications. You wouldn't want to miss a moment of this journey. Trust me, it's going to be quantumly amazing. In this lesson, we will explore the early pioneers, key breakthroughs, and recent developments in the field of quantum computing. Early pioneers. To understand the history of quantum computing, let's think of it as a journey. Imagine you're embarking on a journey to explore a new land. In the early days of quantum computing, several brilliant scientists paved the way for this revolutionary field. One of the early pioneers was Max Planck, who in the early 1900s discovered that energy comes in discrete packets called quanta similar to individual coins. This discovery laid the foundation for the quantum theory. Another notable figure is Albert Einstein, who introduced the concept of the photoelectric effect, which explained how light interacts with matter on a quantum level. Key breakthroughs. As our journey through quantum computing progresses, we encounter key breakthroughs that push the field forward. One such breakthrough was the development of quantum mechanics by Erwin Schrödinger and Werner Heisenberg. They introduced mathematical models and principles to describe the behavior of particles at the quantum level. Schrödinger's famous thought experiment involving a cat in a box highlighted the concept of superposition, where something can be in multiple states simultaneously. Another significant breakthrough was Richard Feynman's proposal of using quantum systems to simulate and solve complex problems that classical computers struggle with. Recent developments. As we reach the more recent parts of our journey, we come across exciting developments in quantum computing. Scientists and engineers have made remarkable progress in building quantum computers with increasing numbers of qubits, also known as quantum bits. IBM, Google, Microsoft, and other companies are actively researching and developing quantum hardware. For example, in 2019, Google's quantum computer demonstrated quantum supremacy by performing a calculation that would take the most powerful supercomputers thousands of years to solve in a matter of minutes. This milestone showed the immense potential of quantum computers. Key differences. Classical computers are like traditional cars that follow traffic rules and move in a straightforward manner. They process information using bits, which are like light switches that can be either on or off, which means 1 or 0. On the other hand, quantum computers are more like magical teleportation devices. They use qubits, which can exist in multiple states at once, like being in multiple places simultaneously. Qubits have a property called superposition, allowing them to represent more than just 0 or 1. This fundamental difference in how information is represented gives quantum computers the potential to perform certain calculations much faster than classical computers. Speed and complexity comparison. Imagine you have a massive library with billions of books, and you need to find a specific word. Classical computers would search through the books one by one until they find the word, which can be time-consuming. Quantum computers, with their ability to process many possibilities simultaneously, would be like having millions of librarians searching through different books at the same time. This parallelism allows quantum computers to solve certain problems exponentially faster. Potential impact of quantum computing. Quantum computing has the potential to revolutionize many fields. For example, in drug discovery, quantum computers can simulate the behavior of molecules more accurately, leading to the development of new medications. Quantum computing can also improve optimization problems, such as finding the best routes for delivery trucks or optimizing financial portfolios. However, not all problems can be solved more efficiently using quantum computers. Classical computers will still excel at tasks like word processing, web browsing, and everyday computing needs. Let's explore the concept of quantum bits, qubits, and understand how they differ from classical bits. Concept of superposition. Imagine you have a coin that you can spin. In classical computing, the coin can only be in one state at a time, either heads or tails. It's like the coin has made up its mind. In quantum computing, a qubit can be in a superposition of states, just like the coin spinning in the air. It can exist in multiple states simultaneously, such as being both heads and tails at the same time. We don't know the exact state until we measure it. Binary states in classical computing versus quantum states in quantum computing. Classical bits are the building blocks of classical computing. They can represent either a 0 or a 1, just like a light switch that is either on or off. Quantum states, represented by qubits, can exist in a combination of 0 and 1 simultaneously. They can be in a superposition, representing both 0 and 1 at the same time. It's like having a light switch that can be in a middle position between on and off. Concept of entanglement. Entanglement is a unique property of qubits that allows them to be correlated in a special way, even when separated by large distances. It's like having two coins that are magically connected, so that when you flip one, the other will always show the opposite result. If you measure one entangled qubit and find it to be a certain state, the other entangled qubit instantly knows its state, regardless of the distance between them. This phenomenon is often referred to as spooky action at a distance and has been experimentally observed. Quantum logic gates. In classical computing, logic gates are like small switches that process and manipulate bits of information. Similarly, quantum logic gates are operations that manipulate qubits in quantum computing. The NOT gate is a basic quantum logic gate that flips the state of a qubit. It's like reversing the polarity of a magnet, turning the north pole into the south pole and vice versa. The CNOT or controlled NOT gate is a 2-qubit gate that flips the target qubit if and only if the control qubit is in a specific state. It's like having a lock that can only be opened if you have the right key. The Toffoli gate is a 3-qubit gate that performs a NOT operation on the target qubit only if both control qubits are in a specific state. It's like having a security system that requires two people to enter their passcodes simultaneously to unlock a door. Building quantum circuits. A quantum circuit is a series of quantum gates that manipulate qubits to perform calculations. Think of it as a roadmap that guides the flow of information within a quantum computer. Quantum circuits are constructed by connecting quantum gates in specific sequences and arrangements. It's like assembling a set of puzzle pieces in a particular order to create a desired pattern. The input to a quantum circuit is typically a set of qubits in specific initial states, and the output is obtained by measuring the final states of the qubits after applying the gates. Comparison with classical gates and circuits. Classical gates, such as the AND, OR, and NOT gates, manipulate classical bits using Boolean logic. They process information in a sequential and deterministic manner. Quantum gates, on the other hand, operate on qubits in a superposition of states, allowing for parallel processing and probabilistic outcomes. Quantum circuits can perform certain calculations much faster than classical circuits, thanks to the unique properties of qubits, such as superposition and entanglement. In this lesson, we will provide an overview of some prominent quantum algorithms and their applications. We will explain Grover's algorithm, Shor's algorithm, and the concepts of quantum teleportation and quantum key distribution or QKD. Let's break it down using relatable examples and analogies. Grover's algorithm. Grover's algorithm is a quantum search algorithm that can efficiently find an item in an unsorted database. Imagine you have a room with many drawers, and you need to find a specific item. In classical computing, you would need to check each drawer one by one. However, with Grover's algorithm, it's like having a magical flashlight that illuminates the correct drawer instantly. By using quantum superposition and interference, Grover's algorithm can perform the search much faster than classical algorithms. Shor's algorithm. Shor's algorithm is a quantum algorithm that can efficiently factor large numbers. Factoring large numbers is crucial for cryptography, and classical algorithms struggle with this task for very large numbers. Shor's algorithm is like a powerful mathematical wizard that can break down a large number into its prime factors quickly. By leveraging the principles of quantum computing, Shor's algorithm can solve the factoring problem exponentially faster than classical algorithms. This has significant implications for breaking current encryption schemes and has led to interest in post-quantum cryptography, quantum teleportation and quantum key distribution, or QKD. Quantum teleportation is a protocol that allows the transfer of quantum states from one qubit to another, even if they are physically separated. It's like having a magic trick where you can instantly make an object appear in a different location. Quantum key distribution, or QKD, is a secure communication method that utilizes the principles of quantum mechanics to exchange encryption keys between two parties. It's like having a secret language that only the intended receiver can understand, ensuring secure communication. Understanding these quantum algorithms showcases the power and potential of quantum computing. Grover's algorithm and Shor's algorithm demonstrate how quantum algorithms can outperform classical algorithms in specific tasks. Quantum teleportation and QKD highlight the unique features of quantum communication, enabling secure information transfer. As quantum computing continues to advance, these algorithms and concepts open up exciting possibilities for solving complex problems and enhancing communication and security protocols. Introduction to vectors and matrices. Imagine you have a shopping list with different items. Each item can be represented as a vector, which is like an arrow pointing in a specific direction. The length of the arrow represents the magnitude, and the direction represents the item's properties or features. Matrices are like grids or tables that organize multiple vectors together. Just like a spreadsheet with rows and columns, matrices allow us to store and manipulate multiple vectors simultaneously. Bracket notation. In quantum computing, a common notation used is called bracket notation, represented as psi. It's similar to expressing an inner product between two vectors. The psi vector, called the bra vector, represents the conjugate transpose of the psi vector, called the ket vector. Think of the bra vector as the row vector and the ket vector as the column vector. Tensor product. The tensor product is a mathematical operation that combines two vectors or matrices. It's like merging two separate shopping lists into a single, larger list. For example, if you have one vector representing colors and another vector representing sizes, the tensor product will create a new vector that combines both color and size information. Definition and properties. In quantum computing, operators are mathematical entities that describe transformations or operations on quantum states. They are like instructions or actions that we can perform on qubits. Quantum operators have properties such as linearity and unitarity. Linearity means that the operator can be applied to a combination of quantum states, similar to how you can apply the same cooking recipe to different ingredients. Unitarity ensures that the operator preserves the total probability of the quantum state. Pauli matrices. Pauli matrices are a set of three 2x2 matrices, sigma x, sigma y, and sigma z. Each matrix corresponds to a specific type of quantum operation that can be performed on a qubit. Sigma x is like a flip or rotation around the x-axis, similar to rotating an object to its side. Sigma y is like a flip or rotation around the y-axis, similar to rotating an object to its back. Sigma z is like a phase shift or flipping the sign of the state, similar to changing the direction of an arrow. Unitary, permission, and projection operators. Unitary operators are special types of quantum operators that preserve the length and orthogonality of quantum states. They can be thought of as reversible transformations, like a perfectly reversible machine. Permission operators are self-adjoint operators, meaning they are equal to their own conjugate transpose. They have real eigenvalues, which represent measurable quantities in quantum mechanics, such as energy levels. Projection operators project a quantum state onto a specific subspace, like focusing a beam of light onto a particular area. Finite and infinite dimensional Hilbert spaces. Hilbert spaces are mathematical spaces that describe the states of quantum systems. Think of a Hilbert space as a playground where quantum states can exist and interact. Finite-dimensional Hilbert spaces are like a set of rooms, each representing a specific quantum state. The number of rooms corresponds to the number of dimensions in the Hilbert space. Infinite-dimensional Hilbert spaces are like a vast landscape with infinitely many possible quantum states. They allow for more complex and continuous representations of quantum systems. Inner product and outer product. In Hilbert spaces, an inner product is a mathematical operation that measures the similarity between two quantum states. It's like determining how similar two vectors are by looking at their alignment and magnitude. The outer product, also known as the tensor product, combines two quantum states to create a composite state. It's like combining two separate puzzles into a larger, more complex puzzle. Projection operators in Hilbert space. Projection operators play a vital role in Hilbert spaces and quantum mechanics. They are like filters that extract specific information from a quantum state. For example, imagine you have a bag of colorful marbles, and you want to separate the red marbles from the rest. The act of picking out only the red marbles can be seen as a projection operation, isolating a specific subset from the whole. State space. In quantum mechanics, a state describes the properties and characteristics of a quantum system. It's like a snapshot that captures all the relevant information about the system. Think of a state space as a vast landscape where each point represents a unique quantum state. Just as different positions in a landscape have different properties, different points in the state space correspond to distinct quantum states. Evolution. Quantum systems evolve over time according to specific rules. This evolution is often described using a mathematical equation called the Schrödinger equation. Imagine a pendulum swinging back and forth. The motion of the pendulum can be described mathematically, and in a similar way, the Schrödinger equation describes how a quantum state changes and evolves. Quantum measurement. Quantum measurement is the process of extracting information from a quantum system. When we measure a quantum property, the state of the system collapses to one of the possible measurement outcomes. Consider a box with an unknown object inside. When you open the box, you determine the object's identity, and the mystery is resolved. Similarly, in quantum measurement, we obtain specific information about the quantum state by performing measurements. Concept and definition. Quantum entanglement is a phenomenon in which two or more particles become connected in such a way that the state of one particle is instantly correlated with the state of another, regardless of the distance between them. Imagine two entangled dice. When one dice is rolled and shows a particular number, the other dice, no matter how far apart it is, will always show the complementary number. This instantaneous connection is a characteristic of entanglement, Bell states and Bell's theorem. Bell states are a set of four maximally entangled quantum states that demonstrate the phenomenon of entanglement. Bell's theorem, proposed by physicist John Bell, shows that no local hidden variables can explain the observed correlations in entangled quantum systems. In other words, the entanglement cannot be explained by any pre-existing information or communication between the entangled particles. Quantum non-locality. Quantum entanglement exhibits non-locality, meaning that the entangled particles can influence each other's states instantaneously, regardless of the distance between them. It's like having two synchronized clocks that always show the same time, no matter how far apart they are. Even if one clock is on Earth and the other is on the Moon, any change to one clock's time will be immediately reflected in the other clock. Discrete Fourier transform in classical computing. The discrete Fourier transform, or DFT, is a mathematical operation used in classical computing to analyze and transform signals or data from the time domain to the frequency domain. Consider a music track with various instruments playing different notes simultaneously. The DFT can help identify the individual frequencies of each instrument, separating them to understand their contribution to the overall sound. Quantum Fourier transform. The quantum Fourier transform, QFT, is a quantum version of the Fourier transform that operates on quantum states. It allows us to transform a quantum state from a basis of position or time to a basis of frequency. Imagine a musical instrument that can play multiple notes at the same time. The QFT can analyze this combined sound and extract the individual frequencies, similar to understanding the composition of a chord. Applications: phase estimation, order finding. The QFT finds various applications in quantum algorithms. One significant application is phase estimation, which allows us to estimate the phase of a quantum state with high precision. It has applications in quantum simulations and solving problems related to periodic phenomena. Another application is order finding, which is used in Shor's algorithm for factoring large numbers. It helps determine the period of a function, which is crucial in finding the factors of a number efficiently. Overview and problem definition. Shor's algorithm is a quantum algorithm devised by mathematician Peter Shor in 1994. Its primary purpose is to factorize large composite numbers efficiently. Factoring large numbers is challenging for classical computers, especially when the numbers are products of two large prime numbers. Shor's algorithm aims to solve this problem using the power of quantum computing. Steps in computational complexity. Shor's algorithm involves several steps, including quantum and classical components. Quantum Fourier transform, or QFT. It performs a Fourier transform on quantum states, enabling precise estimation of periodicities. Quantum modular exponentiation. It efficiently calculates modular exponentiations, a crucial step in finding the period of a function. Classical post-processing. It analyzes the measurement outcomes obtained from the quantum computations to determine the factors of the large number. The computational complexity of Shor's algorithm is significantly lower than classical factoring algorithms. While classical algorithms take exponential time, Shor's algorithm can factorize large numbers in polynomial time, providing a substantial speedup. Impact and current status. Shor's algorithm sparked immense interest because it demonstrated a quantum advantage over classical computers in a practical application. However, implementing Shor's algorithm on large-scale, fault-tolerant quantum computers remains a significant challenge due to the need for a large number of high-quality qubits and precise quantum operations. As a result, there is ongoing research and development in both quantum hardware and error correction techniques to make Shor's algorithm and other quantum algorithms practical and scalable. In this lesson, we will explore Grover's algorithm, a quantum search algorithm that can efficiently find a specific item in an unsorted database. Let's break it down using relatable examples and everyday scenarios. Overview and problem definition. Grover's algorithm, named after mathematician Love Grover, is a quantum algorithm designed to search an unsorted database or solve the unstructured search problem. Imagine you have a large room filled with boxes, and you need to find a specific box without any labels or organization. Grover's algorithm provides a quantum approach to tackle this challenging search problem efficiently. Steps in computational complexity. Grover's algorithm involves the following steps. Initialization. The quantum system is prepared in a superposition of all possible states, representing potential solutions. Oracle. An oracle, a quantum function, marks the target item by inverting its phase. It helps identify the desired item within the database. Amplitude amplification, a process of repeatedly applying a transformation that amplifies the amplitude of the target item and reduces the amplitudes of other items. Measurement. Finally, a measurement is performed, collapsing the system into the state representing the solution. The computational complexity of Grover's algorithm is efficient, providing a quadratic speedup compared to classical algorithms. While classical algorithms require an average of n/2 steps to find the desired item in an unsorted database of n items, Grover's algorithm requires roughly square root n steps, significantly reducing the search time. Designing an efficient quantum oracle is crucial in Grover's algorithm. The oracle identifies the target item within the database and marks it for efficient search. It's like having a magic light that shines on the exact box you're looking for in a dark room, making it stand out from the others. Problem statement. Quantum phase estimation addresses the task of determining the phase of a quantum state with high precision. The phase contains valuable information about the state and is often related to measurable quantities such as energy levels or frequencies. Consider a pendulum swinging back and forth. The phase of the pendulum represents its position in the oscillation cycle, which can reveal information about its motion. Implementation. Quantum phase estimation uses a combination of quantum and classical components. Quantum state preparation. The algorithm starts by preparing a quantum state that contains the phase information to be estimated. Quantum Fourier transform. The QFT is applied to the prepared state, similar to how the Fourier transform analyzes frequency components of a signal. Measurement and classical post-processing. The output of the QFT is measured, and classical post-processing techniques are employed to extract the phase information. Applications in other quantum algorithms. Quantum phase estimation serves as a crucial subroutine in various quantum algorithms, enabling efficient calculations and simulations. It plays a pivotal role in Shor's algorithm for factoring large numbers, where estimating the phase allows for the determination of the period of a function. In quantum chemistry simulations, quantum phase estimation is utilized to determine the energy levels and properties of molecular systems. Concepts and protocol. Quantum teleportation. Quantum teleportation is a protocol that allows the transfer of quantum states from one location to another without physically moving the qubits themselves. It relies on the phenomenon of entanglement to achieve this transfer. Superdense coding. Superdense coding is a protocol that enables the transmission of classical information using quantum states. It takes advantage of the entanglement and shared prior entanglement between sender and receiver. Implementation. Quantum teleportation. Preparation. The sender, Alice, and the receiver, Bob, share an entangled pair of qubits. Measurement and communication. Alice performs measurements on her qubit and sends the measurement results to Bob classically. Bob's operation. Based on Alice's measurement results, Bob applies specific quantum operations to his qubit to recreate the original state that Alice wanted to teleport. Superdense coding. Initialization. Alice and Bob share an entangled pair of qubits. Encoding. Alice applies specific quantum operations on her qubit to encode classical information, known as a quantum state, onto the entangled pair. Transmission. Alice sends her qubit to Bob using a classical communication channel. Decoding. Bob applies specific quantum operations on his qubit to decode the transmitted information, retrieving the original classical message. Potential applications and limitations. Quantum teleportation enables secure communication and serves as a building block for more complex quantum communication protocols. Superdense coding can enhance the efficiency of classical information transmission in scenarios where the quantum channel is available. However, both protocols have practical limitations due to the fragility of entanglement and the need for reliable quantum operations and quantum channels. Need for error correction in quantum computing. Quantum systems are highly sensitive to noise and disturbances from their environment. Even small interactions can introduce errors and cause information loss in quantum states. Imagine you are trying to read a book in a noisy room where some letters are randomly changed or erased. Error correction in quantum computing is like having a mechanism that automatically detects and corrects those errors, allowing for reliable computation. Quantum noise and decoherence. Quantum noise refers to unwanted disturbances that affect quantum systems, such as fluctuations in temperature, electromagnetic fields, or imperfections in hardware components. Decoherence is the process by which a quantum system loses its coherence and becomes entangled with its environment. It causes the delicate quantum information to degrade rapidly. Bit flip and phase flip errors. In quantum computing, two common types of errors are bit flip and phase flip errors. Bit flip error. It occurs when the value of a qubit flips between 0 and 1 due to noise. It's like a light switch randomly changing its state. Phase flip error. It occurs when the phase of a qubit, represented by the sign of its quantum state, flips. It's like the sign of a number randomly changing between positive and negative. Shor code. The Shor code is one of the most well-known and widely used quantum error correction codes. It can detect and correct errors caused by bit flip and phase flip errors. Think of the Shor code as a redundant encoding of quantum information. It adds extra qubits to the original qubits, forming a larger code space to detect and correct errors. Steen code. The Steen code is another popular quantum error correction code that provides even greater protection against errors. It can detect and correct errors caused by bit flip, phase flip, and certain combinations of both. Imagine a team of redundant workers checking each other's work for errors. The Steen code employs a similar idea of redundancy and error detection to ensure accurate quantum computation. Surface codes. Surface codes are a family of quantum error correction codes that offer high error protection and scalability. They can detect and correct errors caused by bit flip, phase flip, and certain multi-qubit errors. Picture a checkerboard where each square represents a qubit. By checking the parity of neighboring qubits, surface codes can identify and correct errors, similar to how a missing or flipped checker on the board can be detected and corrected. Concept and need for quantum fault tolerance. Quantum fault tolerance refers to the ability of a quantum computing system to perform accurate and reliable computations despite the presence of errors and noise. Imagine building a robust bridge that can withstand external forces like wind or earthquakes without collapsing. Similarly, quantum fault tolerance aims to build quantum systems that can handle errors and disturbances without compromising the integrity of the computation. Threshold theorem. The threshold theorem in quantum fault tolerance states that if the error rate of individual quantum operations falls below a certain threshold, arbitrarily long and accurate quantum computations can be achieved by using error correction techniques. It's like having a maximum tolerance for errors in a manufacturing process. As long as the error rate is below the threshold, the overall quality of the product remains high. Implementations and challenges. Implementing fault-tolerant quantum computing is a challenging task due to various factors, such as the need for error correction codes, the requirement for reliable qubits and quantum gates, and the impact of error propagation. Overcoming these challenges involves developing better error correction codes, improving qubit coherence and gate fidelities, and minimizing error propagation through error mitigation techniques. It's akin to constructing a complex system with redundancies, robust components, and error detection mechanisms to ensure its stability and reliability. Definition and properties. Stabilizer codes are a family of quantum error correction codes that can detect and correct errors caused by certain types of noise, including bit flip and phase flip errors. The key idea behind stabilizer codes is the use of stabilizer operators, which are sets of Pauli operators that commute with each other and with the code's encoded states. Think of stabilizer codes as a set of checks or tests that can identify errors in a system. By measuring the stabilizer operators, we can determine whether errors have occurred and correct them. Gottesman-Nil theorem. The Gottesman-Nil theorem is a powerful result that states that stabilizer codes can be efficiently simulated on classical computers. This means that the computations involved in measuring stabilizer operators and applying error correction can be done efficiently using classical algorithms. It's like having a detailed blueprint of a complex structure that allows us to understand and simulate its behavior without needing to physically construct it. Applications in quantum error correction. Stabilizer codes form the basis for many error correction protocols in quantum computing, including popular codes like the Shor code and the surface codes. These codes can detect and correct errors by measuring stabilizer operators and applying appropriate corrections based on the measurement outcomes. Stabilizer codes are particularly useful in the context of fault-tolerant quantum computation, where the efficient measurement and correction of errors are essential. Topological quantum codes. Topological quantum codes are a class of quantum error correction codes that exploit the topological properties of quantum states to protect against errors. Think of a puzzle with pieces that interlock in a specific way. Changing or flipping one piece affects the overall structure, allowing errors to be detected and corrected. Topological codes encode quantum information in such a way that errors manifest as topological defects, which can be detected and corrected. Topological quantum states. Topological quantum states are quantum states that exhibit robustness against local perturbations and noise due to their topological properties. Imagine a rope tied in a knot. Regardless of small deformations in the rope, the knot remains intact. Similarly, topological quantum states are resistant to local noise and errors. Topological quantum codes and operations. Topological quantum codes are typically defined on two-dimensional lattices or surfaces, such as the toric code or surface codes. Error correction in topological codes involves performing measurements on groups of qubits to detect and correct errors. These measurements rely on the topological properties of the code. It's like having a map with landmarks that guide you to correct errors. By observing the relationships between these landmarks, errors can be identified and corrected. Advantages and challenges. Topological quantum error correction offers several advantages, including the ability to correct a wide range of errors, inherent fault tolerance, and robustness against local noise. However, implementing topological codes requires precise control over qubits and their interactions, as well as the ability to create and manipulate topological states. These pose significant experimental challenges. Basics of cryptography. Cryptography is the science of secure communication and involves techniques to protect information from unauthorized access or tampering. Think of cryptography as sending a secret message to a friend using a code that only you and your friend understand, keeping the message hidden from others. Quantum key distribution, or QKD. Quantum key distribution is a method of generating and sharing encryption keys securely using quantum properties. Imagine you and your friend each have a pair of entangled dice. By rolling the dice and comparing the results, you can generate a shared secret key. Even if someone intercepts the dice, the entanglement ensures that the shared key remains secure. BB84 Protocol. The BB84 protocol, developed by Charles H. Bennett and Gilles Broussard in 1984, is a popular quantum key distribution protocol. It involves encoding information on individual quantum particles, such as photons, using two non-orthogonal bases, example, vertical and diagonal polarization. Through measurements and comparisons, the sender and receiver can establish a shared key while detecting any potential eavesdropping attempts. Quantum cryptography advantages. Quantum cryptography offers several advantages over classical cryptographic methods: security against eavesdropping. Quantum mechanics ensures that any attempt to intercept or measure quantum states will disturb them, alerting the communicating parties to potential eavesdropping. Information theoretic security. Quantum cryptography provides information theoretic security, which means the security of the communication is based on fundamental physical principles and cannot be compromised by computational advances. Quantum eavesdropping strategies. Eavesdropping refers to unauthorized interception of communication with the intention of extracting information. In quantum cryptography, eavesdropping can be attempted through various strategies, such as intercepting and measuring quantum states, or introducing noise to manipulate the information. Quantum privacy amplification. Privacy amplification is a technique used in quantum cryptography to ensure that any information obtained by an eavesdropper becomes negligible. Imagine you have a secret code, and someone overhears a few words. By applying privacy amplification techniques, you can transform the remaining information into a new secret code, rendering the eavesdropped information useless. Unconditional security proof. One of the remarkable aspects of quantum cryptography is the concept of unconditional security, which means that the security of the communication can be guaranteed against any computational power or technological advances. Through the principles of quantum mechanics, quantum cryptography ensures that any eavesdropping attempts will be detected, and the shared key will remain secure. Quantum cryptography protocols. Quantum cryptography protocols, such as quantum key distribution, QKD, incorporate measures to detect eavesdropping attempts and maintain the privacy of communication. By utilizing quantum properties, such as the non-cloning theorem and the no-signaling principle, these protocols enable secure key exchange without revealing information to potential eavesdroppers. Quantum repeaters. Quantum repeaters are devices used to extend the range of quantum communication by overcoming the limitations of quantum systems and noisy channels. Imagine a relay race where multiple runners pass a baton to cover a longer distance. Quantum repeaters act as intermediate stations that receive and retransmit quantum information to enable long-distance quantum communication. Quantum network protocols. Quantum communication networks rely on protocols for the secure transmission and distribution of quantum information. One example is the quantum key distribution, or QKD protocol, which allows for the secure exchange of encryption keys using quantum properties. Another protocol is quantum teleportation, which enables the transfer of quantum states between distant locations. Challenges in current research. Building practical quantum communication networks faces several challenges. Maintaining quantum coherence over long distances. Quantum information is susceptible to noise and decoherence, making it challenging to transmit reliably over extended network spans. Establishing secure connections. Quantum networks require secure channels to protect against eavesdropping and ensure the privacy of quantum information. Current research focuses on developing efficient quantum repeater technologies, quantum network protocols, and improving the overall reliability and security of quantum communication networks. Quantum authentication protocols. Quantum authentication protocols are designed to verify the identity of communicating parties and ensure secure communication channels. Think of it as a system where you need to present a valid identification card to gain access to a restricted area, ensuring that only authorized individuals can enter. Quantum digital signatures. Quantum digital signatures are cryptographic techniques used to verify the integrity and origin of digital messages in quantum communication. Imagine you receive a package with a tamper-evident seal and a signature from the sender. The seal ensures the package's integrity, while the signature confirms that it came from the claimed sender. Security proofs and practical considerations. Quantum authentication and digital signature protocols are designed to provide provable security based on the principles of quantum mechanics. Researchers develop security proofs to demonstrate that these protocols are resistant to various attacks, ensuring their reliability and effectiveness. Additionally, practical considerations such as the efficiency of the protocols and their compatibility with existing cryptographic systems are important factors in their adoption. Threat of quantum computers to current cryptographic systems. Quantum computers have the potential to break many of the cryptographic systems currently in use, such as RSA and ECC, elliptic curve cryptography. Imagine a lock on a door that can be easily picked using a powerful tool. Similarly, quantum computers can efficiently solve certain mathematical problems that form the basis of current cryptographic algorithms. Post-quantum cryptographic approaches. Post-quantum cryptography focuses on developing cryptographic algorithms that are secure against attacks by both classical and quantum computers. These approaches often rely on mathematical problems that are believed to be computationally hard for both classical and quantum computers. Think of it as replacing the vulnerable lock on the door with a new, more secure lock that cannot be easily picked, even by powerful tools. Lattice-based, code-based, multivariate polynomial cryptography. Lattice-based, code-based, and multivariate polynomial cryptography are examples of post-quantum cryptographic approaches. Lattice-based cryptography uses the computational complexity of problems involving lattices, while code-based cryptography relies on error-correcting codes and the difficulty of decoding. Multivariate polynomial cryptography utilizes the algebraic properties of multivariate polynomials to create secure cryptographic systems. Quantum-resistant algorithms. Post-quantum cryptographic algorithms are designed to withstand attacks by both classical and quantum computers, providing long-term security. These algorithms aim to ensure that even with the advent of powerful quantum computers, the confidentiality and integrity of sensitive information are preserved. Think of it as future-proofing cryptographic systems to withstand the potential threat of quantum computers. In this lesson, we will explore quantum programming languages, which are specialized languages used to program quantum computers. Let's break it down using relatable examples and everyday scenarios. Qubit representation in software. Quantum programming languages provide ways to represent and manipulate qubits, which are the fundamental units of information in quantum computing. Think of qubits as a set of switches that can be in multiple states simultaneously, similar to a combination lock with multiple dials. Basic operations in quantum programming. Quantum programming languages offer a set of operations to manipulate qubits and perform quantum computations. These operations include quantum gates, which are analogous to logic gates in classical computing and allow for transformations of qubits. Quantum simulators. Quantum programming languages often come with simulators that allow users to simulate quantum computations on classical computers. Simulators are like virtual laboratories where you can experiment with quantum programs and observe their behavior without the need for a physical quantum computer. Examples of quantum programming languages. Qiskit is a popular open-source quantum programming framework developed by IBM. It provides a comprehensive set of tools and libraries for programming and simulating quantum computations. Microsoft Q#. Microsoft Q# is a programming language designed for quantum computing, integrated with the Microsoft Quantum Development Kit. It offers a high-level and scalable approach to quantum programming. Cirq is a quantum programming library developed by Google. It provides a Python framework for creating and running quantum circuits, enabling researchers and developers to experiment with quantum algorithms. Installing and setting up Qiskit. To start programming with Qiskit, you need to install Qiskit on your local machine or use an online environment provided by IBM. Think of this step as installing a software development kit or SDK on your computer, which provides you with the necessary tools to write and run quantum programs, building and executing quantum circuits. Qiskit uses the concept of quantum circuits, which are sequences of quantum gates that manipulate qubits to perform computations. Similar to assembling Lego blocks to build a structure, you can use Qiskit to construct quantum circuits by selecting appropriate gates and connecting them to form a circuit, implementing simple quantum algorithms. Qiskit allows you to implement various quantum algorithms using its programming interface. For example, you can implement the famous quantum algorithm called Grover's algorithm using Qiskit to perform a faster search in an unsorted database. Running simulations. Qiskit provides a built-in simulator that allows you to simulate the behavior of quantum circuits on classical computers. This is like using a flight simulator to experience the feeling of flying without leaving the ground. With Qiskit's simulator, you can observe the behavior of quantum circuits and analyze the results. Installing and setting up Q#. To start programming with Q#, you need to install the Microsoft Quantum Development Kit, which includes the Q# programming language and necessary tools. Think of this step as setting up a specialized software development environment that enables you to write and run Q# programs, building and executing quantum circuits. Q# allows you to define and manipulate quantum circuits using a high-level programming interface. Similar to writing code in a programming language, you can use Q# to create quantum circuits by specifying quantum operations and their parameters, implementing simple quantum algorithms. Q# provides a rich set of libraries and functions that allow you to implement various quantum algorithms and experiments. For example, you can implement algorithms like the quantum teleportation or Grover's search algorithm using Q# to solve specific problems, running simulations and interfacing with classical code. Q# supports running simulations of quantum programs on classical computers, allowing you to debug and test your code. Additionally, Q# enables seamless integration with classical code, allowing you to combine quantum and classical computations within a single program. Quantum resource estimation. Q# provides tools for estimating the required quantum resources, such as qubits and gates, for executing quantum algorithms. This allows you to assess the feasibility and resource requirements of your quantum programs and algorithms. Introduction to libraries like Cirq, Strawberry Fields. Quantum computing libraries such as Cirq and Strawberry Fields provide high-level abstractions and tools for programming quantum algorithms. Think of these libraries as toolboxes filled with specialized tools for constructing and executing quantum circuits. Comparison of different quantum computing libraries. Different quantum computing libraries have varying features, programming interfaces, and target architectures. It's like comparing different brands of power tools. Each may have unique features and specifications that cater to different needs. Integration with classical computing software. Quantum computing libraries often offer APIs and tools to interface with classical computing software and frameworks. This allows you to combine quantum algorithms with classical computations, leveraging the strengths of both paradigms. Think of it as connecting different components of a larger system to work together seamlessly, leveraging quantum computing libraries for efficiency. Quantum computing libraries are designed to optimize and streamline quantum computations, making them more efficient and accessible. They provide functions and abstractions that simplify complex operations and enable efficient execution on different quantum hardware architectures. Quantum algorithm design. The quantum software development lifecycle begins with the design of quantum algorithms to solve specific problems. Think of this phase as architecting a blueprint for a building, where you define the overall structure and functionality of the quantum algorithm. Coding and simulation. Once the algorithm design is finalized, the next step is coding the quantum algorithm using a suitable quantum programming language like Qiskit or Microsoft Q #. You can then simulate the behavior of the quantum algorithm using a simulator, such as Qiskit's built-in simulator or other available tools. Simulation is like building a virtual prototype of a machine before constructing the physical device, allowing you to test and validate the algorithm's behavior. Debugging and testing. During the coding and simulation phase, you may encounter errors or unexpected behavior in your quantum program. Debugging involves identifying and fixing these errors by examining the code and analyzing the program's execution. Testing involves running the quantum algorithm on different inputs and scenarios to ensure its correctness and performance. Refinement and optimization. After debugging and testing, you may refine and optimize your quantum algorithm to improve its efficiency and performance. This could involve optimizing gate sequences, reducing the number of required operations, or exploring alternative algorithmic approaches. Integration with classical computing. Quantum algorithms often interact with classical computing systems for pre-processing, post-processing, or interfacing with classical data. Integrating the quantum algorithm with classical computing software or frameworks is an important step in the software development lifecycle. Ion traps. Ion traps are a physical system used to implement qubits by trapping and manipulating individual ions using electric and magnetic fields. Think of it as capturing individual marbles using a magnetic field and manipulating their positions to encode information. Superconducting qubits. Superconducting qubits are implemented using superconducting circuits that can carry electrical current without resistance. Imagine a loop of wire made of a superconducting material that can oscillate between different energy states, representing the qubit states. Photonic qubits. Photonic qubits use photons, particles of light, to encode and manipulate quantum information. Think of it as using light signals, such as different polarizations or photon counts, to represent the different quantum states of the qubit. Challenges in physical implementation. Physical implementation of qubits faces several challenges, including decoherence. Qubits are sensitive to their surrounding environment, causing loss of quantum information due to interactions with noise and disturbances. Error correction. Protecting qubits from errors and preserving their quantum states is crucial for reliable quantum computation. Scalability. Scaling up the number of qubits and maintaining their coherence becomes increasingly challenging as more qubits are added to a quantum system. Single qubit operations. Single qubit gates operate on a single qubit and can rotate its state in different ways. Think of it as adjusting the position of a compass needle by applying different rotations to it. Two qubit operations. Two qubit gates operate on a pair of qubits and enable interactions between them. Imagine two interconnected gears that can influence each other's movement, representing the interaction between two qubits. Higher order operations. Higher order quantum gates involve 3 or more qubits and enable more complex computations. It's like a group of interconnected gears that collectively perform intricate mechanical operations. Implementation technologies. Different physical implementations of qubits utilize various technologies to implement quantum gates. For example, superconducting qubits use microwave pulses to control and manipulate qubit states, while ion trap systems use laser beams to apply gate operations. Concept of quantum volume. Quantum volume is a metric used to measure the computational capability of a quantum computer. Think of it as the capacity of a container that determines how much information or computation a quantum computer can handle. Quantum processor architectures. Quantum processors are designed using different architectures, each with its advantages and challenges. Examples include circuit-based architectures, example, qubit arrays connected by quantum gates, and adiabatic architectures, example, using quantum annealing to solve optimization problems. Challenges in scaling quantum computers. Scaling up quantum computers to handle larger numbers of qubits and more complex computations is a significant challenge. It's like expanding a road network to accommodate increased traffic without causing congestion or compromising efficiency. Quantum error correction. Quantum computer architectures often include error correction techniques to mitigate the effects of noise and errors in qubits. Error correction is like using redundancy or backup systems to ensure accurate transmission of information, despite potential errors or disruptions. Introduction to quantum annealing. Quantum annealing is a technique that utilizes quantum effects to solve optimization problems more efficiently than classical algorithms. Think of it as using a special tool or method specifically designed for optimizing complex systems or finding the best solution among multiple possibilities. Concept of quantum supremacy. Quantum supremacy refers to the point where a quantum computer can perform a specific computational task faster than any known classical computer. Imagine a scenario where a new type of vehicle surpasses all existing vehicles in terms of speed, reaching a level of performance that was previously considered impossible. Google's Sycamore processor. The Google Sycamore processor is a notable example that demonstrated quantum supremacy in 2019 by performing a task that would take classical supercomputers an impractical amount of time. This achievement highlighted the potential of quantum computers to solve certain problems exponentially faster than classical computers. Implications and challenges. Quantum supremacy has important implications for cryptography, optimization, and other fields where classical computers struggle to find efficient solutions. However, achieving and maintaining quantum supremacy at larger scales and for more practical problems remains a significant challenge due to factors such as noise, error rates, and scalability. Sources of quantum noise. Quantum noise can arise from various sources, such as interactions with the environment, imperfections in hardware components, and limitations in control mechanisms. Think of it as background noise in a phone call that can distort the voice signal and make it difficult to understand the conversation clearly. Effects of quantum noise on computations. Quantum noise can cause errors in qubit states, introduce decoherence, loss of quantum information, and affect the accuracy of quantum operations and measurements. It's like trying to perform precise measurements while standing on a vibrating platform, which can introduce uncertainties and distort the results. Strategies for noise mitigation. Researchers employ various strategies to mitigate the effects of quantum noise and improve the reliability of quantum computations. Error correction codes, such as the ones used in quantum error correction, can detect and correct errors caused by noise, similar to error correcting codes used in classical systems. Error rates and thresholds. Error rates indicate the likelihood of errors occurring in quantum computations, and threshold values define the maximum error rate tolerable for reliable quantum computation. It's like setting a threshold for the acceptable level of errors in a manufacturing process, beyond which the products may become faulty or unreliable. In this chapter, we will explore the intersection of quantum computing and machine learning, known as quantum machine learning or QML. Quantum machine learning combines the principles of quantum mechanics with classical machine learning techniques to develop novel algorithms and models. Quantum-enhanced machine learning algorithms. Quantum machine learning aims to leverage the unique properties of quantum systems to enhance machine learning algorithms. Think of it as upgrading a traditional tool with advanced features to improve its performance and capabilities. Quantum neural networks. Quantum neural networks are a class of quantum machine learning models inspired by classical neural networks. They use quantum states and quantum operations to perform computations and extract features from data. Imagine a network of interconnected neurons that can process information using quantum effects, leading to potentially more efficient learning and inference. Quantum support vector machines. Quantum support vector machines, or QSVM, are quantum algorithms that can be used for classification tasks. They exploit quantum properties to find optimal decision boundaries in high-dimensional feature spaces. Think of it as finding the best way to separate different types of objects in a complex, multi-dimensional space using quantum algorithms. Quantum feature maps. Quantum feature maps are transformations that convert classical data into quantum states. Think of it as a translator that converts information from one language, classical data, to another, quantum states. Quantum data encoding. Quantum data encoding is the process of representing classical data in quantum states, often using qubits. It involves mapping classical information onto quantum systems to take advantage of quantum computational capabilities. Imagine converting a sequence of binary digits into a series of quantum states, where each state represents a specific bit value. Quantum kernels. Quantum kernels define the similarity or dissimilarity between pairs of quantum states. They play a crucial role in quantum machine learning algorithms, such as quantum support vector machines. Think of it as a measure of how similar two quantum states are, which helps in performing classification or regression tasks. Quantum version of k-means clustering, principal component analysis. Quantum machine learning algorithms offer quantum versions of classical algorithms such as k-means clustering and principal component analysis, or PCA. These quantum algorithms take advantage of quantum properties to potentially provide improved performance or efficiency compared to their classical counterparts. Think of it as using an advanced version of a familiar algorithm that can process data more effectively by leveraging quantum properties. Quantum Boltzmann machines. Quantum Boltzmann machines are quantum counterparts of classical Boltzmann machines, which are used for unsupervised learning and generative modeling. They utilize quantum states and quantum operations to explore complex probability distributions and learn patterns from data. Imagine a machine that uses quantum effects to better understand the underlying patterns in a dataset and generate new samples based on that understanding. Variational quantum eigensolver, or VQE, for machine learning. The variational quantum eigensolver, or VQE, is a quantum algorithm used to estimate the lowest energy state of a given Hamiltonian. It has applications in solving optimization problems relevant to machine learning. Think of it as a specialized algorithm that leverages quantum capabilities to find the best solution to a complex optimization problem, which can be useful in machine learning applications. Software packages for quantum machine learning. Several software packages and frameworks are available to support quantum machine learning research and development. These packages provide tools, libraries, and APIs for implementing and running quantum machine learning algorithms. Think of it as a toolbox filled with specialized tools and resources to facilitate quantum machine learning tasks. Challenges and limitations. Quantum machine learning is an emerging field, and there are several challenges and limitations to consider. These challenges include the limited availability of quantum hardware, noise and error rates in current quantum systems, and the complexity of mapping machine learning problems onto quantum algorithms. Imagine trying to solve a complex problem with limited resources and imperfect tools. It requires careful consideration and creative problem solving. Potential applications and use cases. Quantum machine learning has the potential to impact various domains and industries. It can be applied to areas such as drug discovery, materials science, optimization problems, financial modeling, and pattern recognition. Think of it as using advanced tools to gain new insights and solve problems in fields where classical methods may struggle to provide efficient solutions. Current research and open problems. Researchers are actively investigating various aspects of QML, including the development of new algorithms, improving error mitigation techniques, and exploring the theoretical foundations of QML. Open problems in QML include finding efficient ways to map classical machine learning problems onto quantum algorithms, improving training techniques for quantum neural networks, and exploring the limits of quantum advantage in machine learning. Quantum advantage in machine learning. Quantum advantage refers to the scenario where quantum machine learning algorithms outperform classical algorithms for specific tasks. Achieving quantum advantage in machine learning is an ongoing research goal, and it has the potential to revolutionize various applications by solving problems faster or with better accuracy. Quantum machine learning in the NISQ era. The NISQ era represents the current stage of quantum computing technology, where noise and error rates in quantum systems are relatively high. During this era, QML can still be valuable by leveraging quantum systems for specific tasks that benefit from quantum properties, such as quantum simulation, quantum chemistry, or optimization problems. Think of it as utilizing a prototype or early version of a technology to perform specific tasks and gather insights before the technology reaches its full potential. Congratulations on completing the Quantum Computers course on CogniPlus. You've reached the end of this exciting journey. Keep exploring the fascinating world of quantum computing and let your curiosity guide you to new horizons. Best of luck in your future endeavors. Don't forget to subscribe to the channel for more exciting content on quantum computers and stay updated with the latest advancements in this groundbreaking field. Happy learning and thank you for being a part of our community.